Our modern world depends on a hidden network in the sky. Satellites circle our planet, silent and busy. They help us talk on our phones. They guide our cars through unfamiliar streets. They watch our weather. They send us images of distant galaxies. These orbital helpers are essential, yet they live in a very dangerous neighborhood. Space is not empty. It contains countless tiny objects, like grains of sand or small pebbles, moving faster than any bullet. A hit from one of these tiny bits of debris can cause serious damage to a satellite's delicate skin. The dangers don't just come from physical objects. Our sun is an active star. It sometimes sends out massive bursts of energy and charged particles, known as space weather. These solar storms can flood a satellite's electronics with radiation, causing them to fail. Protecting our orbital assets is a huge challenge. Traditional shields are like heavy armor. They are often thick, rigid, and add a lot of weight. If this armor gets damaged, it cannot be fixed. Sending a repair mission is incredibly expensive and often impossible for satellites in high orbits. We need a smarter, more flexible solution. What if a satellite could wear a shield that was light? What if that shield could repair itself after a small impact? Imagine a protective layer that could change its shape on command. This is the core problem we are trying to solve. We need a new kind of defense for our eyes and ears in the sky. The answer might not be a solid wall, but something more dynamic and alive. This essay explores a new concept, a shield of tiny, smart liquid tiles that assemble in the vacuum of space. A system less like armor and more like a living skin. It would be a shield that can form when needed, heal its own wounds, adapt to changing conditions. The concept uses simple principles of magnetism and chemistry to create a complex and responsive defense. It is an exploration into what might be possible for the next generation of satellite protection. Let's journey into this idea step by step. The story begins with a problem, but it points toward a fascinating potential solution. At the very heart of this conceptual shield are the M-BUTs. The name stands for Biphasic Utility Tiles. Think of them as smart, liquid building blocks. Each M-BUT is a tiny droplet of specialized fluid encased in a flexible, responsive skin. They are the bricks that will build our space shield. Inside each droplet are countless nanoscale magnetic particles. These particles are like tiny compass needles that all point in the same direction when the satellite sends out its magnetic guiding beam. This is what allows the satellite to steer the tiles through space. The skin of each M-BUT tile is where much of the magic happens. It isn't just a simple container. It is a complex membrane made of special molecules that can change their shape. When the satellite applies a specific electric field, these molecules reorient themselves. This action causes the spherical droplet to flatten out into a tile-like shape, ready to connect with its neighbors. This ability to change from a sphere to a flattened disk is crucial for creating a smooth, connected surface with very few gaps. The skin is what makes a simple droplet into a functional tile. When two M-BUT tiles are guided next to each other, they don't just bump and float away. The satellite's field encourages them to lock together. Their specialized skins are designed to form a quick but sturdy connection, a process known as supramolecular coordination. At the exact moment they bond, a tiny flicker of light can be seen. This is a harmless visual effect, a tiny sparklet created by the energy released as the molecules snap into their new, stable configuration. The M-BUT tiles form the structure, but what gives the shield its strength and its signature glow? Ferroflux. Cyanoluminol. Ferroflux is the substance inside each tile that gives the shield its ability to become rigid on command. It is a special type of fluid known as a magnetorheological liquid. It can change its viscosity almost instantly when a magnetic field is applied. In its normal state, ferroflux is a thick fluid, allowing the shield to be flexible. When the satellite needs to harden the shield, it adjusts the magnetic field, passing through the tiles. tiny iron particles within ferroflux align and form chain-like structures. The alignment stiffens the liquid into a near solid in milliseconds. The shield goes from a flexible skin to a rigid plate. This is magneto-rheological stiffening, like turning water into ice with the flip of a switch. While ferroflux provides strength, cyanoluminol gives visual confirmation the shield is healthy. Cyanoluminol is a photonic ionic sol, a gel-like substance that glows. It sits in the spaces between the M-but tiles and around the M-but tiles. As tiles snap together, the gel percolates through tiny channels. Electrical currents, when tiles bond or ambient light, cause cyanoluminol to emit a soft cyan glow, photoluminescence. The glow isn't just for looks, it's a vital status signal. Brightness maps directly to how many tiles are connected. As the shield grows, the glow intensifies and spreads. A uniform bright cyan means fully formed, gap-free coverage. Damaged sections glow less or go dark, instantly mapping faults. For the M-but tiles to form a perfect, gapless shield, their edges must connect with precision. This is the job of amphiscale, Linkion. Amphiscale is a type of molecule called an amphiphile, which lives on the very edge of each tile's skin. One end of the molecule is attracted to the tile's skin. The other end can be changed by the satellite's electric field. This lets the system precisely control the shape and behavior of tile edges. Think of amphiscale as a way to control how tiles wet each other, like a droplet spreading or beading. Satellite sends a signal that flips amphiscale orientation. Edges flatten and spread, creating a wide, tight seal with a neighbor. In animations of the concept, this looks like the tiles have tiny wings that can unfurl to create a perfect connection. Close-up labeled, amphiscale wings unfurling, and Linkion bridges forming with a tiny spark. Once two tiles are brought side by the magnetic field, Linkion steps in to lock them together. Linkion is a thin ionic docking fluid film between the tiles. It's filled with charged particles, ions. The satellite field encourages these ions to form weak electrical bonds, creating ionic bridges. These bridges act like a microscopic zipper, securely fastening the tiles together. The connection is strong enough to hold, but weak enough to be unzipped by the satellite if reconfiguration is needed. The formation of these ionic bridges is what creates the tiny, harmless sparks of light when tiles connect. As the ions move into place, they release a tiny flash of light. This phenomenon, called plasmonic sparklets, photoluminescence, it's the click you can see. Beyond structure and function, the liquid tile shield concept includes elements that provide important visual information and optical properties. One of these is nanopap, a component that acts as the shield's pigment. Nanopap consists of tiny, flat crystals called nanoplatelets that are mixed into the tile's skin. These platelets are designed to interact with light in specific ways. Their primary job is to give the shield a particular color or shimmer, which can be useful for managing heat from the sun. By reflecting certain wavelengths of light, they can help keep the satellite cool. The nanopap platelets are also responsive. The satellite's electromagnetic field can slightly alter their orientation. This allows the satellite to change the optical properties of its shield on the fly. For example, it could make one part of the shield more reflective to deflect intense sunlight, while making another part less reflective. In some versions of the concept, these nanoplatelets also contribute to the tiny sparks seen when tiles connect. Rapid changes in the local electromagnetic field can cause them to create brief plasmonic bursts, flashes of light that are both beautiful and informative. So, how does this all come together in the vacuum of space? The process begins with the satellite identifying a need for its shield. It might be a pre-programmed maneuver, or a response to a warning from a space weather monitoring service. The satellite opens a small hatch on its storage tank. It releases a controlled number of M-but tiles. At first they float nearby as a disorganized cloud of tiny spheres. Then the satellite activates its phased electromagnetic field emitter. The emitter is the conductor's baton for assembly. The field is shown as dashed lines, or as a gentle, pulsing wave of light emanating from the satellite. The beam is patterned with gradients, stronger areas, weaker areas. Magnetic particles inside the M-butt tiles are drawn along these gradients. The tiles slide into position along invisible tracks. Meanwhile, the beam's electrical component signals the tile skin to flatten. A tile approaches its designated spot next to an already placed tile. Local fields intensify. That pulls the two tiles together. Amphiscale molecules on their edges unfurl for a flat, wide connection. Link-ion fluid between them forms ionic bridges, zipping the tiles together. A small, harmless spark flashes at the moment of connection. The tile is now part of the growing shield. The process repeats, tile by tile, at incredible speed. A wave of sparks ripples across the satellite's surface as the shield expands. Simultaneously, cyanoluminol gel percolates through new channels. A soft cyan glow appears and spreads, following the assembly wave. The glow brightens as coverage becomes more complete, forming a translucent, luminous shell. The satellite's computer monitors the glow to track progress. Once the glow is uniform and reaches the desired intensity, the satellite knows the shield is fully deployed and ready. The successful assembly of the liquid tile shield brings a host of benefits. The most significant advantage is its ability to heal. In the harsh environment of space, small impacts from micrometeoroids are inevitable. With a traditional solid shield, each impact leaves a permanent scar. That weakens the overall structure. With the M-butt shield, the system can respond. Damaged tiles can be detached by the satellite by reversing the fields holding them in place. A fresh tile from the reserve tank is guided in to fill the gap, restoring the shield to full integrity. Another major payoff is adaptability. A satellite's needs can change. It might need a clear line of sight to point a sensitive instrument at a distant star. The satellite commands the shield to reconfigure, creating a temporary window by moving tiles aside. When the observation is complete, the tiles move back into place. The shield's rigidity can be adjusted. During normal ops, it stays flexible to save energy. If a solar storm approaches, the satellite activates ferroflux, and the shell rigidifies for max protection. The system is incredibly lightweight compared to traditional armor. The tiles are stored as a dense liquid and deployed only when needed. That reduces launch mass, a major mission cost. A lighter satellite means a cheaper launch. A lighter satellite can carry more scientific instruments. A lighter satellite can carry more fuel. The shield is not dead weight. It's a functional, multi-purpose system. The cyan glow is a low-power, high-visibility indicator of shield health. Finally, there's potential for on-orbit recycling and reuse. Tiles could be collected, tiles could be stored, tiles could be redeployed across missions or satellites in a fleet. That moves us closer to sustainable space exploration, self-healing, reconfigurability, low mass. It transforms protection from a static defense into a living, breathing function of the satellite itself. It is crucial to remember that this vision of a self-assembling liquid shield is, for now, a concept. It is an idea born from the principles of nanoscience and materials engineering, but it is not yet a flight-ready technology. The journey from a conceptual design to a working prototype is long and filled with challenges. Each component of the system would need to be developed and tested rigorously in labs on Earth before ever being trusted in space. M-butt tiles, ferroflux, cyanoluminol, and the others. The first steps would involve creating and testing the materials themselves. Can we synthesize M-butt tiles that reliably change shape and respond to magnetic fields? Does the link-ion fluid form stable yet reversible bonds in a vacuum? We would need to measure the light from the sparks to ensure they are truly harmless, and do not interfere with the satellite's sensitive electronics. The long-term stability of these materials in the harsh radiation and extreme temperatures of space would need to be studied extensively. Safety and reliability are paramount. Beyond the materials, the control system itself presents a significant engineering challenge. Designing a phased electromagnetic emitter that is precise enough to guide millions of tiny tiles into a complex three-dimensional shape requires sophisticated software and hardware. The system must be robust and fail-safe. We must ensure that the guiding fields do not disrupt other critical satellite functions. These are not trivial problems, and they will require years of dedicated research and development to solve. However, every great leap in technology begins as a bold idea. The concept of a living, healing shield for satellites gives us a new direction to explore. The next steps are clear. Begin the foundational lab work, test each component in simulated space environments, use computer modeling to refine the assembly process. While we are not ready to deploy these shields tomorrow, this idea pushes the boundaries of what we imagine is possible for protecting our vital assets in orbit.